Hi, yeah, thanks to the organisers for giving me the opportunity to speak here. This is joint work with Ashley Montanaro and Changpeng Zhao, and everyone was at the University of Bristol at the time this work was done. And the paper is called Testing Quantum Satisfiability. So I'll begin by introducing what quantum satisfiability is. So just some notation first of all. I'll write n in square brackets for the n element set, and I'll write sigma sub k of n for the set of all k element subsets of the n element set. So the cardinality of this set is n choose k. And for any k element subset within this, for any k element subset, we'll use this overline notation to represent the complement in the L element set. So that's just some notation first of all. And I'll just leap straight in and define what this problem of quantum k-sat is. So you have n qubits, q1 to qn. And for every subset of k of the qubits, you have a constraint. So that's a projection, a Hermitian projection on those qubits. So yeah, for every subset of k qubits, you have a projector on those k qubits. And we say that this constraint is satisfied for some state of all the n qubits together if you have this projector, right, which is on those k qubits, S, you do the projection, and on everything else you do nothing at all. And you want this state of the n qubits to be in the kernel of this projection here. So we say that the constraint is satisfied if this state is in the kernel of that projection. And the problem is as follows. So for every k element subset of the qubits, you have one of these constraints, and you want to know whether there's some state of all the n qubits which satisfies all the constraints together. So you can write this as you just take the sum of all these projectors. So you've got the projector acting on the subset. Take the sum for every k element subset, and you want the state to be in the kernel of this sum. So why would you want to consider this problem? Well, in the language of physics, this is equivalent to deciding whether a k-local Hamiltonian is frustration-free. It's also QMA1 hard, and if you add a promise that there's a gap for the ground state energy, then this problem is QMA1 complete. So it's an interesting problem to consider. So that's quantum k-sat. And it's obviously a hard problem, so normally people use sort of focus on special cases. So here we're going to focus on the dense case where there's many projectors, and we're going to use a property testing approach. So I'll explain what I mean by property testing approach now. In computer science, you often want to check whether a structure, such as an instance of quantum k-sat, possesses a global property such as being satisfiable. And the idea of property testing is that you want to do this by performing local checks on small subsets of the data defining the structure. But in general, you might have the problem that the structure doesn't have the property, but it's close enough to having it that this isn't witnessed by any of the local checks. So what you usually have is a promise, the structure has the property, or it's far from having the property, where far is defined by some constant. And then you can use this approach. So Alan and Shapiro showed that classical Boolean satisfiability was amenable to a property testing approach, which was the starting point of this paper. We were interested in knowing whether quantum Boolean satisfiability had the same sort of, you could use a property testing approach for that too. So that's the outline of the problem, and so now I can tell you our results. So for property testing, right, you need a notion of what it is to be far from having the property, far from satisfiable in our case. And the notion of far from satisfiable we use is epsilon far from satisfiable by a product state. So you've got an instance of quantum k-sat, and we say that it's epsilon far from satisfiable by a product state for some constant epsilon if you have to remove more than epsilon n to the k of the constraints before the instance becomes satisfiable by a product state. So formally what I mean by that is, if you've got some subset of the constraints, such that if you only consider projectors that aren't in that subset, then there's a product state in the kernel of all those projectors, then you know that the cardinality of this set of projectors you've removed has to be greater than epsilon n to the k. So notice we're talking about a product state here, epsilon far from satisfied by a product state, and this is better. So it makes our results stronger because you need to remove more projectors to be satisfiable by a product state than you need to move to be satisfiable by any state. So more instances of quantum k-sat fall into this notion of epsilon far from satisfiable by a product state. So that's the notion of far we use, and then we're going to be doing these local checks. So what are the local checks? So we're going to be checking local satisfiability by a product state. So if you've got an instance of quantum k-sat defined by some projections, and you take a subset of the n qubits, then we say that the instance is locally satisfiable by product state on that subset if there exists some product state of those qubits, such that if you only consider constraints which only act on qubits in that subset, so you only consider the constraints acting just on qubits in that subset, then this product state is in the kernel of all those constraints. So this is the notion of local satisfiability we use. And note that while being unsatisfiable, epsilon far from satisfiable by product state, there's a global property involving all the constraints on all the qubits. This is a local property involving only a subset of the constraints, which only act on a certain subset of the qubits. So those are our definitions, and then we have these two theorems. So theorem one is that if you're globally satisfiable, then you're locally satisfiable by a product state with high probability. So say you've got some instance of quantum K-SAT, which is satisfiable, and then you fix some constant greater than or equal to 3, and we're going to choose a subset of the qubits uniformly at random of that size, of size C. Then the probability that the instance is locally satisfiable by product state on that subset is greater than P whenever n is big enough. So whenever n is bigger than this number psi pc, which is the order of 2 to the 6 c over log 1 over p. So whenever n is big enough, you're locally satisfiable on constant size subsets by a product state, if you're satisfiable globally. The case C equals 2 also holds, but in this case, the results are much stronger and easier to prove. I won't talk about that in the talk, but it's in the paper. That's theorem 1. And then theorem 2 is that, that's the other way around, that if you're epsilon far from satisfiable by a product state, then you're locally unsatisfiable by a product state with high probability. So there exists some constant, ck epsilon, so it only depends on k and epsilon, it doesn't depend on n. Such that if you have some instance of quantum K-SAT, which is epsilon far from satisfiable by a product state, and you choose a random subset of this size of the qubits, then the instance will be locally unsatisfiable by a product state with high probability in this case. The weakness of our result is that we don't have a good upper bound on this constant. We do have an inner upper bound, but it's enormous. But the point is it doesn't depend on n, which from the point of kind of complexity is all we need. So given these two theorems, the corollary is that if you have the promise that it's either satisfiable or epsilon far from satisfiable, you can solve quantum K-SAT using a classical computer in time polynomial in n. So the proof is very simple. By theorem 1, if it's satisfiable, then it's locally satisfiable by a product state on constant size subsets with high probability. And by theorem 2, if it's epsilon far from satisfiable by a product state, then it's locally unsatisfiable by a product state on constant size subsets with high probability. So all you need to do is check satisfiability by a product state on randomly chosen constant size subsets, and this can be done using Grosvenor basis methods. So that's the high level picture of the results in the paper. And in the remainder of the talk, I'd just like to talk about the proofs of theorem 1 and theorem 2. So the proof of theorem 1, here's a restatement of theorem 1, that if you have a satisfiable instance of quantum K-SAT, you choose a subset of constant size uniformly at random, then the instance will be locally satisfiable by a product state with high probability as long as n is big enough. So you can change this into a statement about quantum states, and that's the first step in the proof. So here's a statement about quantum states. You have this is equivalent to theorem 1. If you have any state of n qubits, and then you choose a subset of constant size uniformly at random, then you consider this subspace here. So basically you trace out all the qubits that aren't in this subset, and you get a density matrix on the qubits in that subset. And then you take the support of this density matrix. So you can think of the support as being the span of the eigenvectors associated to non-zero eigenvalues of the density matrix. And this subspace is the subspace of the C qubit Hilbert space. And then you want to know whether this subspace contains a product state. So the probability that the subspace does contain a product state is greater than P whenever n is big enough. So you can rephrase a statement about local satisfiability as an equivalent statement about states. So we need to prove this statement about states. So how are we going to do this? Well, the key is to use a result from entanglement theory, which is already known. So if you have a qubit tensor a q dit, where d for some d, then we say that the subspace is completely entangled if there's no product state in the subspace. So there's this theorem here that if you have a completely entangled subspace of a q bit tensor something else, then the orthogonal complement contains a product state. So this is a proposition that's known. And note that this doesn't apply for d greater than or equal to 3 if you've got a q dit tensor something else. So this immediately restricts our result to q bits. So using this proposition, we can prove the kind of key lemma in our proof. which is the following. If you've got a state of n qubits and you pick one of the qubits, and then you partition the remaining qubits into two subsets. So just like this here. Here we've chosen subsets of equal size, but they don't have to be of equal size. It can be any bipartition of the remaining qubits. Then at least one of the following things is true. The first one is if you trace out the qubits in S2, then you get a product state. Then the support of the density matrix on what's left contains a product state over X in S1. Or if you trace out the qubits in S1, the support of the density matrix that's left contains a product state in X or something, an X and something in S2. So one of those two, at least one of those two things is true. Then using this lemma, we can prove the theorem. So what we're going to do is we take any state, and we're going to pick this randomly chosen constant size subset. We're going to pick the qubits one by one. Then we're going to perform some analysis that shows that indeed the support of this partial trace density matrix will contain a product state with high probability. So the way we do this is we pick the first qubit, and then we consider the set of all the remaining n-1 qubits. And then we consider all let's suppose n-1 is even for simplicity. It's just a bit of a subtlety if it's not. And we consider all the equal bipartitions of the remaining qubits. So the bipartitions into two sets of equal size. So there's n-1 choose n-1/2 of these. Now, by the lemma we just saw, for any of these equal bipartitions, if you trace out one of the sets, you'll get a product state on what's left. So that's true for at least one of the two sets in every bipartition. So we end up with a n-1/2 regular hypergraph on a set of qubits not equal to x1, with edge density greater than a half, such that for any edge of this hypergraph, we have that this support, if you trace out everything not qubit x1 or the edge, contains a product state. So you repeat this analysis, you pick the qubits x2 to xc-1, and you repeat this analysis, and you end up with a regular hypergraph on the set of qubits not equal to x1 to xc-1, such that for every edge of this hypergraph, if you trace out everything that's not equal to x1 to xc-1 on the edge, you have a product state on what's left. And so looking at this hypergraph, you can conclude that if you pick the last qubit xc and it lies within an edge of this hypergraph, then this support here contains a product state. And so you can lower bound this probability by lower bounding the edge density and edge size of this hypergraph. So that's the way we prove the theorem 1. So that's theorem 1. And then on to theorem 2. So theorem 2 is, just to remind you, there exists some constant not depending on n, such that the following holds. If you've got an instance of quantum k-sat, which is epsilon far from satisfiable by product state, then a randomly chosen subset of this size will be locally unsatisfiable by a product state with high probability. So the proof of this closely follows the proof of Allen-Shapiro, but we weren't able to directly kind of take everything from the proof of Allen-Shapiro, as we'll see. It was kind of slightly non-trivial to quantize. So the idea, what we're going to be doing basically is we're going to be thinking about extending assignments. So we're going to have a local assignment on some subset of the qubits, and we're going to think about extending these local assignments. So just some notation, if you've got a subset of the qubits, we'll write H sub x for the Hilbert space of that subset of the n qubits. So we've got this notion of local assignments. So if you have some instance of quantum k-sat defined by these projections, and you fix some subset of the qubits S, then we say that an assignment on that subset is a product subspace of the Hilbert space of those qubits, such that for every state in that product subspace, we have that if you only consider constraints which act on just qubits in this subset, then every state is in the kernel of those constraints. Every state satisfies those constraints. So we write SPS for the pair of the subset and the assignment. So if you have an assignment to some subset of the qubits and some other qubit not in that subset, you might be able to extend it to an assignment on S in this qubit in the kind of obvious way. You pick some subspace of the Hilbert space of that qubit and just tensor it with the assignment. But you might not be able to do this. So there's two ways this can go wrong. So if you've got an instance of quantum k-sat and some assignment on some subset, we say that a qubit conflicts with the assignment if you can't extend the assignment to that qubit. But there's another way it could go wrong. It could be heavy with respect to this local assignment, in the sense that if you extend this assignment to that qubit, it'll greatly reduce the number of possible extensions to the other qubits. And there's a way to formally define this, which is a really nice kind of combinatorial ansatz of Allen-Shapiro, but it's a bit complicated to state in this talk. So you can formally define what this is, and if a qubit is either heavy or conflicting, we say that it's bad. So we have two lemmas, which are direct analogs of lemmas of Alan-Shapiro, proved in a very similar way. So that if we say that a chain of length m is an assignment on m qubits, which can be obtained by continuously extending the empty assignment through heavy qubits. So basically, every qubit here is heavy with respect to the assignment came before it. So if the qubit m is heavy with respect to the assignment p1 to pm minus 1, and so on down to the bottom. And lemma 1 says that if you have a chain of sufficient length, this length 5 times 4 to the k minus 1 over epsilon, then every qubit will be conflicting with respect to the chain. So basically, you can't continue extending through heavy qubits. At some point, you have to stop. That's lemma 1. And then lemma 2 is that with respect to any assignment, there are always going to be many bad qubits. So if you have an instance of quantum K-sat, which is epsilon far from satisfiable, and you have any kind of assignment on some subset of the qubits, then there are going to be at least epsilon n over 5 bad qubits with respect to that assignment, regardless of what the subset and the assignments are. So using these two lemmas, in the classical case, it's quite straightforward to prove the theorem. So basically, you pick bits one by one randomly, and you construct a binary tree of possible assignments to those bits. And if a given branch of the tree goes through enough bad variables, then by lemma 1, we will have to stop because you can't go through too many bad variables. And then by lemma 2, you've got many bad variables with respect to any assignment, so each branch will go through enough bad variables after this constant number of rounds. So you can conclude that after that number of rounds, the instance will be locally unsatisfiable with high probability. Of course, you can't apply this directly in the classical case because you can't build a binary tree, and this is the problem with quantizing Alan-Shapiro's proof. In the quantum setting, the space of possible assignments to a qubit is a Hilbert space. It's not a two-element set. So the way we get around this problem is to use a backtracking approach. So we pick qubits at random, and we extend an assignment until you can't extend it any further. And then we'll pick some more qubits, and then we'll eliminate, in order to eliminate all possible assignments of the qubits we've already picked. So that's the idea of the backtracking approach. But of course, we still need to discretize because we can only eliminate finitely many assignments, so we still need to discretize. And to do this, we use some ideas from algebraic geometry. And I'll just finish by stating the lemma from algebraic geometry that we do use for this discretization. So if you've got a state of a qubit, we'll use this angular bracket notation for the corresponding point on the Bloch sphere. And then we define this. So suppose we've got a subspace of an m-qubit Hilbert space. We define a set X, which is a set of all points on the Bloch sphere which extend to a product state in this subspace. Another way to say this is that there exists it's the point on the Bloch sphere such that there exists a product state in the subspace, such that if you take the point on the Bloch sphere corresponding to the first factor of this product state, that's this point X. So it's all the points on the Bloch sphere that extend to something in the product state in the subspace. Then there's this dichotomy that either X is everything in the Bloch sphere, or X is a finite set whose cardinality is bounded above by m factorial, and the bounding case 2 is tight. So this can be proven using known results on the degree of intersections of algebraic varieties, and the use of this lemma restricts our results to qubits. The main reason for that is that the only projective subvarieties of the projective line are the projective line of finite sets, whereas that's not true for high-dimensional projective spaces. So again, we're restricted to qubits. We saw restriction to qubits for theorem 1. Now we see it for theorem 2. And that's basically the way we prove it. So just to conclude, so we've shown that given the promise that an instance of quantum K-sat is either satisfiable or far from satisfiable by a product state, the instance can be solved efficiently on a classical computer. So possible extensions of this result. Does it hold for qubits? We saw this limitation to qubits in the proof. Also, can we improve this upper bound on ck epsilon? There's an analogy with classical property testing here. They used to have really bad upper bounds, but eventually new techniques were found in order to improve them, so that maybe some hope. Also, this kind of falls in the ballpark of quantum property testing. In particular, it's classically testing properties of quantum structures. And there are other quantum structures, such as quantum graphs, for instance, which it might be interesting to apply a property testing approach to. So that's all. Thanks for listening.
If there's any question, there's a microphone over there in the middle. So yeah, let's wait for more questions to come. But so does this means that all the hardness for this problem really lies in this gap of the promise, like in between epsilon far?
Well, yeah, yeah. I mean, it shows that if you have this promise that uh, it's either satisfiable or far from satisfiable, and the problem becomes easy. So the hardness of the problem really lies in not not having too many not having this promise. There's another gap in the definition of QSAT. Usually, there's a gap in the ground state energy, which makes it QMA1 complete. And here we didn't actually use that gap at all. So that gap doesn't come up in this. We didn't need it. So what we solved is actually a kind of harder problem than QSAT as it's usually defined.
I see. And also another question is, do you see like for example you mentioned like physical motivation for quantum satisfiability in like testing if things are frustration free and so on. Do you know of like how well could these approaches be used and
Yeah, I don't actually know kind of what Hamiltonians people actually want to test in physics to know if they're frustration free, but it may be that if they contain many sort of projections that force local entanglement, for instance, then it would be possible to check efficiently whether they're frustration free or not using this proof.
I kind of have a basic question. So it felt to me that you can also define this epsilon satisfierness from a product state for classical KSAT, for example.
Yeah.
But classical KSAT obviously is not in P. So like what is the catch here?
Um. So obviously, if you're just talking about classical KSAT, then the kind of notion of the product state doesn't really apply because everything's a product state. Right?
Yeah, but then you can like just by PCP you can say that like for a 3-sat instance you can say that it's going to be like 7/8 far or like 1/8 far in that sense, right? Because you only have product states. So or I guess I have to be missing something, but I was just wondering why it doesn't apply.
Yeah, for the classical result, um, yeah. So classically, the classical analog of this result is that if you're epsilon far from satisfiable in the sense that you have to move on the order of n to the k of the constraints in order to obtain a solution, then you can solve it efficiently classically. It's got to, but it's got to be on the order of n to the k. Maybe that makes the
Okay.
the difference here.
Thank you.
Hi. I was wondering if there's a way to tweak the promise a little bit to make the problem, say, BQP complete. So to get some sort of separation between quantum and classical.
Right. So oh right, I see. You mean like so QSAT is QMA1 complete if you have the promise gap, and we've shown that if you have this promise that it's epsilon far from satisfiable, it's solvable in randomized polynomial time. So you're asking if maybe the promise was weakened slightly, you could make a QP complete. Yeah, it's interesting. I haven't really thought about it. So yeah, it'll be interesting to think about. Yeah. Thanks.
if there's no more further question, let's thank the speaker again.